Okay, we're going over another method of solving for a system of linear equations. In this case, we are going to use the method of matrix. So the three examples we are going to go over are over here. To use the matrix method, you want to recall the standard form of linear equations, which is capital A times X plus capital B times Y equal capital C, where capital A, B, C are just any real numbers. So the goal is to come up with a 2 rows by 3 column augmented matrix that represent our given system of linear equations, and we want to reduce that matrix down to the reduced row echelon form, RREF matrix, with the same dimension, 2 rows by 3 columns. So in example 1, we have the system of linear equation of positive 2x minus y equal 9 and positive 3x plus y equals 6. Well, immediately we can tell that the augmented matrix of this system of linear equations are going to be 2, which is the coefficient that goes with the x. And since these two equations are already in standard form, by the way, we can go ahead and start setting up the augmented matrix. And the next coefficient, capital B sub 1, which is a coefficient that goes with the y, so that's the invisible negative 1 in the first equation. So B sub 1, capital B sub 1 up here, is a negative 1. Capital C sub 1 are the 9. Now for the second equation, capital A subscript 2 is the coefficient 3 that goes with the x in the second equation. Capital B subscript 2 is the coefficient that goes with the y in the second equation. Well, that's the invisible positive 1. So B sub 2 is 1. So capital C subscript 2 is just a positive 6. Now we want to reduce this augmented matrix of this system down to the reduced row echelon form matrix. Well, this will require a lot of quite a lot of mental math and being able to see ahead and being able to keep your numbers being integers as much as possible. And in some situation or in some problem, you're probably going to end up with fraction, and that is still okay. But fractions are going to make it just a tiny bit more difficult to work with. But it doesn't mean that it is not doable. When I show my work here, I'm going to try to keep all of my numbers being integers as much as I can. Now in this case, if I compare my augmented matrix to the row reduced echelon form, I realize that I get the capital 1 right here already. So if I can somehow convert these three numbers into respectively 0, 1, and 0, then that means I'll be able to find my solution for this system. When I think about this, I can easily convert this negative 1 into the 0 by taking row number 2 and add it to row number 1. So R sub 2 is row 2 and R sub 1 is row 1. It's the first row. So what is the new matrix when I'm doing row addition, row subtraction, or row multiplication to reduce each of these rows down to this format? Well, the row that I'm taking to do the multiplication, which is row number 2 in this step, is going to stay the same. So 3, 1, and 6 remain the same. But the row that is being added will change. So row 2 plus to row number 1, we just have to add them respectively. So 3 in row 2, add 2, that's going to give us 5. Positive 1 in row 2, add to negative 1 in row 1 is going to give us 0. And 6 in row 2, add to 9 in row 1 is going to give us positive 15. So hey, I'm taking row number 2, add it to row 1 means row 2 stay the same. And row 1, which is being added again, will change. So my new row 1 is 5, 0, and 15. Now, I get positive 1 and 0 as shown right here. So I had to convert this number 5 and this number 3 into respectively positive 1 and 0. Now I can go ahead and try to reduce number 3 down to 0, but if I were to take that route, I would end up with dealing with fractions. So I'm going to try to reduce positive 5 into positive 1 instead, okay? And that can be easily done because if I take row number 1 and I multiply it by 1 over 5, that means what? Well, when I take a number and I multiply row number 1, and I mean I multiply any row, that means I take this number and I multiply every number of that row. So 1 over 5 times 5, 1 over 5 times 0, and then 1 over 5 times 15. Now, 1 over 5 times 5, that's going to be positive 1. 1 over 5 times 0, well, that's going to be 0. 1 over 5 times 15, which is 15 over 5, which is going to be positive 3. And then, of course, we are not touching row number 2, so row number 2 stays the same. Now, we're almost there. We got 101, 101. So the only thing left is to reduce this number 3 down to 0. To reduce this positive 3 down to 0, well, if I just take negative 3, multiply row number 1, and then add it to row number 2, I would get what I want. Actually, no, I'm going to write it down here instead. This is going to be negative 3 r sub 1 plus r sub 2. All right. So let's see. So again, I'm taking row 1 and I multiply by a number and I'm adding it to row number 2. So that means my row number 1, my first row, stay the same because I'm taking it to do the multiplication and then doing the addition after. If I take negative 3 multiply row 1, meaning I take negative 3 and I multiply every number of the first row, of that row. So negative 3 times 1 is negative 3. Now, adding respectively, negative 3 plus 3, that's going to give me 0. Now, negative 3 times 0, that's 0. So the product 0 at 1, just going to be 1. Negative 3 times 3, which is negative 9, and then negative 9 at 6, that's going to be negative 3. But hey, guess what? We got our reduced row echelon form matrix, 1, 0, 0, 1. So this number 3 and this number negative 3 are our lowercase a and b as shown on top. So that means what? That means we are going to have 1 times x plus 0 times y equals to positive 3. And we got 0 times x plus 1 times y equal to negative 3. But hey, 0 times y is just going to be 0, so we're left with just x equals to 3. And 0 times x is 0, so we're left with just y equal to negative 3. So that means the solution for this system is 3 comma negative 3. So the overall idea is that any row that you're taking any row that you're taking will stay the same. Just add this. And any row that is being added will change. Okay, so in this case, row 1 is being added. So row 1 will change. And you're taking row 2 to do the addition of row 1. So that's why row 2 stay the same. Same thing in this case. You're taking row number 1 to do the multiplication by negative 3 in order to add to row number 2. So that's why row 1 stays the same as shown in here. But because row 2 is being added, that's why row number 2 will change. Okay, and in the step where you're taking only one of the 2 rows and you're multiplying that entire row by a number, of course that row itself will change. Okay, so like in this step, you're taking row number 1, you're multiplying by a number in order to reduce this term down to positive 1. So that's why only row number 1 will change, and row 2, since you're not touching at this step, it stays the same. So I know it's a little confusing, but matrices like that, it's gonna help a lot if you're able to keep all of your numbers as integers as much as you can. And of course, in some situation, you're gonna run into fraction in the middle of your work, but hey, that's still gonna be doable, okay? But it's just gonna be a tiny bit more difficult. Just know that this column here is the column X. This column here is the column Y, okay? So you got 1 times X plus 0 times Y, which is right there. And of course, this is just the right-hand side of the equal sign. All right, so that's why down here, you have 0 times Y plus 1 times X. And then you got that.